Right. Let's check our schedule together. We are here, right? Today is 14th of April, right? So we are here. So we are supposed to talk about this neon, but I don't think we have time to discuss this neon. So let's just skip this neon and talk about this Thumb2. Okay. And later on, if we have time, then we can come back and talk about this neon. But I don't think we have time. Okay. So now let's talk about this Thumb2. Okay. Thumb2. Before we talk about Thumb2, remember this first PowerPoint intro. Cortex A9, right? This Cortex A9, the first PowerPoint. Cortex A9 is providing 3 instruction sets. Remember? So first one is ARM instruction set. And second, sum, and the last one is Jogel, right? For Java bytecode. So first one, ARM. So far, we focused on ARM instructions. So now we want to talk about the second instruction set. But we are not going to talk in detail about instruction itself, right? And but we will talk about how to mix ARM and some instructions together, because some instructions are very similar to ARM instructions. So you can just intuitively write some program, okay, and compile it. If it doesn't compile okay, then you can fix it. Okay, so let's talk about some instructions. Some, okay, some, not some instructions, some feature. What is some? Okay, second instruction set. This one. Okay, this one, Seokjin, can you please? Okay, hold on. Mail and okay, midterm exam. So here, midterm exam, right? 28th of April, 28th. And after that, right? So if you check the calendar. Sure. Why this panel does not disappear? Persistent. Okay, if you check our schedule, then the 3rd of May. Okay, that's okay. 3rd of May is the first class after midterm exam, right? So that will be offline class. Probably that is announced, right? So exam is on 28th, and offline class start from 3rd of May. Okay, I think that is announced in the email, right? Okay. Okay. What do you think? 26. Okay, so no class on 26. Okay, no class 26 and exam, right? And then we have 3 classes remaining before midterm exam. Okay, so do not complain. Do not complain about no class, please. No class 26. Okay, so I'll update. This announcement section. Okay, later on. Okay, this one. Then how about Songmuk? Can you please? Yes. Chanyeong, right? So everything we discussed in the class. Okay, you have to study everything we have discussed until 21st. Next week. Okay. Okay. Can you please?
Some 16-bit instruction set for improved code density. released in 1994 since ARM 7 TDMI. Thumb2 introduced in 2003 since ARM 1156. Major enhancements to Thumb: expand 16-bit instruction set with additional 32-bit instructions, thus a variable length instruction set. Most Thumb instructions are unconditional. Most ARM instructions are conditional. Thumb2 introduced a conditional execution instruction. Goal is to achieve code density similar to Thumb with performance similar to ARM. Thumb EE, Thumb execution environment. We don't cover this. First appeared in 2005 in Cortex-A8. Force instruction set state, making small change to Thumb2. ARM deprecates any use of Thumb EEISA, and ARM v5 remove support for Thumb EE.
Okay, thanks. Some instruction, right? The first one, some little bit of history, right? Some and some2 and some EE. That is deprecated, so you don't have to worry about this some EE, and we will talk about some2. But what is some? Some ARM defined 2-byte instructions. 2-byte, right? So ARM instructions, how big? ARM instruction. ARM instruction is 4-byte in size, right? And some is 2-byte, 16-bit. 16-bit in size, right? That is first introduced 30 years ago. Is it something like 30 years ago, right? And they added some new feature, some enhancement to some, and they named it some2. In some2, some2 is providing two different sizes. Okay, 2-byte instruction and 4-byte instructions. 2-byte and 4-byte. So it is, something like variable instruction set. 2-byte instruction and 4-byte instructions, right? Some2. So the goal is, so why introduces this some2? The goal is trying to catch, two, birds with one stone. What are two birds? The first one is performance. Performance, okay? Performance. Second is code density. So the performance means, execution time, shorter execution time, okay? So you want to reduce execution time, good performance, and also the small code size. That is a small code size, okay? And while so performance and code size, okay? So shorter execution time and small code size with some2 instruction set. So think about that. Think about your live transcription. What is that? Live transcription. What is that? Closed caption. Closed caption. I don't know. What is that? Live transcription is enabled. Who can see this transcript? I don't know. Okay. Okay. So the sum, two instruction. You want to catch these two birds with one stone, right? Think about the sorting application you wrote before, some C program or some other C programs, right? So you use ARM instructions to compile your sorting .c. Then you use ARM instruction set, right? ARM and some two instructions. Okay, compiler is using some ARM instructions and some two instructions. then probably the code size, the binary size would be, I don't know, 10 kilobyte. So if you use sum2 instruction, compiler is using sum2 instruction, the code size would be 8 kilobyte. How about that? Then code size, compare these two, code size is smaller. Okay, code size is smaller. Then the performance, right? If the performance is similar to this one, then we are happy, right? So small code size and similar performance to this binary. So with the sum2, okay, I'm architect try to catch these two birds, right? That is the goal, right? Okay, so and in CPSR register, you can differentiate, you can distinguish. Oh, right. Okay, I see. Okay, so it is showing that script. So it is showing with the J and T, you can distinguish which instruction set ARM is executing, right? JNT00, then CPU, ARM CPU is executing ARM instruction set, okay? And 01, sum2 instruction set, 10 and Jojel instruction set, okay? It is a little bit annoying because it is showing some script to me, okay? Okay, so here we have J and T bit, by setting J and T CPU. You can turn it off on the bottom of Zoom window. How to turn off? Yeah, it is a little annoying because it is popping up. Turn off at the bottom of Zoom window. How to turn off? Here, disable annotation for others. Live transcript. Disable auto translation. Camden, how to turn it off? Can disable means you cannot see, right? I don't want to see my script. Write subtitle. The bottom there, sure. Closed caption. Don't know, where is that? Disable annotation for others. Disable first? I don't know. Disable. Okay. So it's still. Okay, I don't know. Hide subtitle. Okay, this one. Okay, probably better. Okay, in CPSR, okay, with JNT ARM CPU in hardware, distinguish which instruction set ARM is executing, right? Okay, there is one. Then let's talk about this. Cheon, can you please?
Interworking. In ARM, the instruction set change from ARM to Thumb2 or Thumb2 to ARM is called interworking. Switching is done via BX or BLX instruction. BLX level always changes the instruction set. It changes a processor in ARM state to Thumb2 state or processor in Thumb2 state to ARM state. Use BX error to return. BLX RM. If bit 0 of RM is 0, the processor changes to or remain in ARM state. Bit 0 of RM is 1, the processor changes to or remain in thumb2 state and use bxlr to return bxrm. If bit 0 of rm is 0, processor changes to or remain in ARM state. If bit 0 of rm is 1, the processor changes to or remain in thumb2 state.
Okay, thanks. Again, we are not going to talk about some instruction itself, right? Some instructions are very similar to ARM. The machine code format are completely different, but the mnemonic, right? The mnemonic addition, for example, addition R1, R2, R3, that mnemonic is very similar. So we are not going to talk about some instruction set itself. But here we are going to talk about how to switch between how to switch from ARM instruction set to some instruction and back and forth, right? Some to ARM, ARM to some. How to switch between these two instruction sets. That is called interworking, okay? So basically you want to mix ARM instructions and some instructions together in your program, okay? Then how to switch between ARM to some to ARM. That is the topic we will talk about, okay? And typically, ARM instructions, some instructions are typically implemented inside, separated inside the function. So ARM instruction, some function is implementing, some function is translated using ARM instruction, some function are translated using some instructions. So this function wants to call some instruction. Okay, you want to come back. Okay, something like that. So that switching ARM to some to ARM, that switching is done through one of these instructions. Okay, so ARM is providing essentially two instructions, BLX, BLX and BX. Okay, two flavors here, right? BLX, two flavors. You can specify some label, function name, or register. Okay, to call, for example, to call some function, right? Some function, BLX, some the name of that some function. Okay, then this one you specify the location of the function, right? Location of the function in register. Okay. So the name is BLX, name is branch and link, right? BLX, branch and link, right? BL instruction, BL instruction. Then X means exchange. Branch and link, call function, then instruction ISA, change. Instruction says change from ARM to some or or some to ARM. Okay, so two functionality. Let me show you some example code first. Probably this one is better. So you can download this example code. Okay, this one. Okay, then create this project. I already did that for you. So check out this. We have this assembly code. So here we start with ARM instructions. Okay, ARM instructions and BLX instruction. BLX instruction is trying to call a function. Function name is some C test that is defined in this C code. Okay, some test. Okay, some function, right? So you have to use this directive. Okay, so directive means from this point. Okay, from this point you are asking compiler to use some instructions to translate this code. Okay, so we have we have directive, GCC, target, sum. Then you are asking compiler to use some instructions to translate these two functions. Okay, so here look at this now. You have this new directive. Okay, GCC target from this point. From this point, please use instructions to translate this function, that function, and so on to the end. Okay, so here name some C test. Okay, that's the C code. Okay, will be translated using some instruction. Okay, here C test. Okay, let's go back to assembly. So BLX branch and link and instruction set change. Okay, so you are calling this function and your instruction set will be changed from to sum. Okay, so let's go to some C test. Okay, some C test here. So it is doing very simple operation, doing addition operation. Taking this one as an argument. Okay, A argument, then doing addition, then returning C. So return type is int. Okay, very simple code. Then after coming back, what it is doing? It is using BLX instruction. Again, BLX instruction, but it is calling function. Right? Function. Okay. What is that? It's Okay. So it is doing also simple addition. So here, look at this. It is doing addition 1, 1, 2, 2, 3, 3, 4, 3. Okay. And then add this number. So you want to add this one, and return. So what do you expect? The output will be what? One thing I have to explain before expecting answer from you, getting answer from you. So here, let's talk about this. Calling convention. Okay. Calling convention. In calling convention is defining how to pass argument to function. Okay, and how to value, how to pass return value to the caller. We have a caller and callee, right? Example here. So we have a caller and callee. What is caller and callee? This one, this assembly code is a caller, right? So it's main is caller. It's calling this C function callee. Okay, this caller is calling this function. So when you make a function call, you want to pass some argument like this argument into A, one argument. Then the question is how to pass that argument. Okay, the calling convention defines that detailed mechanism. So according to the calling convention, arguments are passed through these 4 registers: R0, R1, R2, R3. So in ARM, you have 16 registers, right? So using these 4 registers, you can pass argument. If you have a more argument, then you can use a stack. Okay, I have 10 argument to pass. Then okay, you have only 4. Then what do I have to do? You have a stack, right? You use a stack. So in this case, you have only 1 argument to pass. So it's very simple. You use R0 register here. So that is why, look at this. That is why I put 1 to R0. I want to pass 1, this 1 to the C function, this sum function. Okay. And then return value, look at this. The result, the return value, you are returning one integer. in this function. Some C test is returning just one integer, right? So return value will be passed through R0 and R1 registers. If you have two, but in this case you have only one to pass. So so R0 will be used. Okay. So look at this explanation. R0, R1, R2, R3, argument, okay, and then result. If you have a more data to pass, then again, use stack. Okay. Okay. So now let's talk about this. Now, let's analyze this code. Okay, function first. Okay, you are passing 1. You are initializing R0 to 1. Okay, then call this function. Okay, so go back to here. Then this, A will contain 1. So here you are adding 1 to that constant. So you get 1 1 2 2 3 3 4 4. You are adding 1. So C will be 1 1 2 2 3 3 4 4. So after executing that code, right, you will have that value because you add 1, right? So you are returning this value to the caller, right? This caller, this assembly code. Then you are calling this C function. Okay, so that return value will be stored in R0 according to the calling convention. Right? R0 contains that value. Okay, so with this R0, you are calling this function. That means you are passing that constant to that ARM function. Okay, so let's go to here. So it is expecting one argument, right? One argument. So you are passing this value. Okay, then add 4 4 this number. So 4 4 3 3 2 2 1 1. So you add these two, then what do you get? 4 5, right? So you are getting this number. Right? So you are returning C to the caller. So going back to assembly code, then R0 will contain this one. Okay. Then that is the one, right? Any question about this function? Simple, example. It's okay. So check out this compiled. If you are, suspicious about this calling convention, still confusing, then you can check out this, compiled binary ELF, right? Let me compile it just in case. Okay, open this ELF. Okay, and search with some C. Okay, so again here, compiled binary. So initialize R1 to R1 with 1. Okay, R0 will have 1. Then calling this function. Okay, check out this function. How that function got translated by compiler, right? So some, right? So check out R0 register. R0 register because we are expecting you are expecting that the argument will be passed through R0 register. So here we have R0. Okay, R0 will be stored at this location. Okay, and next instruction from the same location, right? Same location, you are reading the value and storing to R2. Okay, so that argument R0 is stored in R2. Okay, you are essentially copied R0 to R2. So 1 R2 will have 1. Okay, so next two instructions. Next two instructions are trying to cook up this constant using move instructions. Okay, these two instructions trying to cook up that constant. And next instruction is doing addition. Addition of what? Addition of these two. So R2, we have 1. Okay, so 1, right? 1 is passed, right? Then that is copied here through memory, right? You are storing and reading back. So R3, the constant. You are doing addition, then store into result. Result is stored into the location, then reading back. Okay, then check out this code R0. Then using BX instruction, you are returning back. Okay, we will talk about this return. But the point here, the argument is passed through R0 register, and return value is also passed through R0 register according to calling convention. That is the point here. Okay, so this is a simple code. So try to analyze this code yourself. It's very simple, only few lines of the code, right? Try to analyze this code yourself. And if you look at this, compiled binary, look at this pragma, right? The directive. So you are asking compiler to use some instructions. So check out this. It is 2-byte instruction. Okay. Sometimes 4-byte instruction. 4-byte instruction, right? 2-byte, 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 4-byte. So it is a mix of 2-byte and 4-byte instruction. There is those are some instructions. Some instructions and machine code for that instruction. Machine code for that instruction, right? So the instruction is very similar, but a little bit strange because you have two operands, not source, two operands, right? Looks a little bit strange, right? Let's take a look at this ARM architecture reference manual. Okay, that is explaining everything about ARM and also some instructions. Let me give you just one example. Okay. Please, next time. Okay, so here I know which section we have to look at, A8.8. Okay, so let's take a look at addition instruction. Right, that is most simple operation, right? Addition. How about how about this? Add register. Check out instruction format. Okay, so several instruction format for addition operation, right? This one, this format, 2-byte format, 2-byte format, so this one encoding, and a 4-byte format. A little bit complicated, right? So if you look at this encoding, then try to interpret this encoding. It is using it has 3 operands, right? RM, RN, and RT. But it is using 3 bits. 3 bits. But how come 3 bits? ARM has 16 general purpose registers from R0 to R15, right? That is hardware block diagram, right? So 16 registers. Then you have 3 bits each for source operand, RM, RN, and destination 3-bit. Then how come? You have 16. That means you need at least 4-bit to pinpoint, okay, that register or that register, which register, right? 4-bit to specify source and destination. But some instruction, this specific format, the specific format is using 3-bit only. That means you are allowed to use from R0 to R7. Okay, these 8 registers. Okay, so compiler, ARM compiler. If you use your C code, then some compiler. Okay, some compiler is trying to use only these 8 registers to translate your code. But that is not possible. Then some compiler will use other instruction format. Again, ARM, some compiler, right? Some compiler is trying to use only these 8 registers. For example, if your application program is simple enough, then probably these 8 registers would be enough to run your program. The compiler will figure that out. Okay, but compiler think, okay, these 8 registers are not enough. Then compiler will choose other formats. So here, look at this. 4-bit. This is encoding. 4-byte encoding. Okay, 4-bit for source operand, 4-bit for destination, 4-bit, another source operand, right? So compiler think, okay, these 8 registers are not enough, then probably use that, format, that format, 4-byte format. Okay. So, what else? Some, right? Some. So in this format, right? Look at this. In this format, look at this. Addition, some encoding, right? You have a destination register, 3-bit, source operand, 3-bit, and you can specify small immediate, very small immediate. Okay, destination, second source, and some immediate. Okay, small immediate. So let me write some assembly because I brought that issue. So using here in assembly, right here, to write some instruction, you have to use that also directive. Okay, that means you are asking, okay, that means you are saying, okay, I'm writing program using some instructions. In C, okay, in C, you use that directive. Right? In assembly, you use this directive. Okay, from now on, from this point, I'm going to use some instructions. Okay, so probably here. So let me try to try to write some code. Then probably compiler will generate this machine code. Which one? Add. What if I write R2? So I'm supposed to use, right? I'm supposed to use 3-bit R0 to R7. So R2 is destination. R1 is first source, probably constant, small constant, probably 7. Can you do that? Okay, about that. I'm hoping compiler use that format, this format, to translate this instruction. Hoping. I don't. Okay, so it is trying to compile everything in this. How many projects do we have? 1, 2, 3, 4, 5, 6. Trying to compile everything. That is why it takes time. I think some assembly. I think. No, I failed. Right? Compiler choose to use different instruction, right? Different instruction. So look at this 4-byte instruction, right? So okay, I failed. Okay, let me try another. I don't know what I have to do. So add. Can I force compiler to use that instruction? I don't know. Probably you can test. Okay, very hard. So compiler decided to use that instruction. I think add W, right? Check out this one. Add W. I think this one. That is a 4-byte instruction, right? Compiler is not that smart, right? Compiler can choose 2-byte instruction. Why, 4-byte instruction in this case? Anyway, you can try. So if you scroll it down, can you spot? Okay, this one. This one is 2-byte instruction, right? 2-byte. Probably register. I don't know, this one, probably. Right? 4488. Right? 4, 4, right? 88. Probably this one. Right? Compiler choose to use that one. This one is this format. Right? 4, 4, right? That's 4, 4. Right? Anyway, yeah, you can test. Okay. Okay. So there is one. Let me remove this. Okay. Then. So here again, you call these two functions, and this branch and link with exchange that is calling arm, right? Sorry, sum function, and this one is calling arm function. Let's go back to our PowerPoint. Okay, so we use that instruction, right? BLX and label here. BLX label function name, BLX function name, right? But it says it is changing. It is always changing instruction set. Okay, always changing instruction. It changes processor in ARM state to some state or vice versa, right? Some state to ARM state. Okay, but one thing is very strange, right? Here, you are in ARM at the beginning. You are in ARM state. Those are ARM instructions. Then you are calling some function. So it makes sense. You use BLX instruction to call some function. Then you are return back, okay, to ARM state here. You are returning back to ARM state. Then this one is the problem. This one is calling some function, ARM function, right? You are in ARM state, but you are calling ARM function, but still you are changing instruction set, BLX. That is very strange, right? So check out. Now the secret is in compiled binary. So here, look at this. First function call. You are calling some function that got translated using same BLX instruction. But second function call, you are calling ARM function, ARM to ARM. So compiler says, okay, it doesn't make sense. Okay, I'm going to translate that into actual BL instruction, not BLX. Compiler will figure that out. Okay, so even though you use BLX, compiler changes that instruction to BL. Okay, so when you write assembly program, many times people just use BLX instruction instead of BL, because compiler will take care of everything. Okay, compiler will figure out if you are calling some, then BLX, right? BLX and BLX. If you are calling ARM, then BLX will be changed to BL. So many people just to use, industry, right? Industry people just use BLX instruction to make a function call. Okay? So it is your choice. Okay, it's your option. You can use either BL or BLX, but many people just use BLX. Okay. Then compiler will do the job for you. Okay, let me for now let me execute that code. Probably I don't have to show up the board, but let me download it and show you the execution. Okay. Debug. I created session here. You have to create new session. Okay, session, new session, debug. Okay, so check out these registers. Then we need to check out CPSR register. Okay, because we are doing interworking instruction set change, right? So what do you have to check? Okay. What you have to check is JBit and very small, right? Tbit. Where is Tbit? Okay, here T, J and T, J, 저젤 bit and some bit, J and T bit, right? So let me show this. Right, this one, right? J bit and 저젤 bit and some bit. If 00, then you are executing ARM instructions. Now 0 and 0. That means CPU is ready to execute ARM instructions. Okay. So now let's just initialize some dummy code. It's not doing anything useful. Okay. Just execute, initialize registers and stack pointer too. Okay. And then now R0 register, right? You want to pass 1 to that function. So R0 will be set to 1. Okay. R0 will set to 1. Then you are making a function call. The thing you have to be careful, the bit you have to take a look is J and T. What do you expect? Which bit will be set after calling this function? T bit will be set to 1. So according to this, okay, instruction set change to thumb2, J0 and T1. 0 and 1. So F5, look at this. J bit is 0 and T bit is 1, right? 0 and 1. So ARM now, CPU is ready to execute some instructions. Okay, so okay, now here R0 is 1, this C code. So let me press F5. Okay, so R3 register. So R3 register is set to 11, 22, 33, 44. So you are returning, right? Then what do you expect? Returning, then R0 register will contain that value. According to calling convention and also according to compiled binary. I showed you compiled binary, right? This one. Some C. According to this binary, R3 register, right? R3 register stores the addition output. This addition output. So that is why 1, 1, 2, 2, 3, 3, 4, 4. And then that is copied to R0 register when you return, right? Close curly bracket. So R0 will contain then that value, right? So let's go back to here. So F5. Okay, F5. Then R0. Okay, R0, 1, 1, 2, 2, 3, 3, 4, 4. Then now J and T bit. J is 0 and T is 0. Then means ARM CPU is ready to execute ARM instructions. Okay, ARM state, right? So now you are calling what? ARM function. and passing this R0 as an argument according to the calling convention. Okay, so press F5. Then J and T, no change, right? 0 and 0, no change. So still ARM state. Okay, so ARM function. Then you are doing addition. Okay, with this value 1 1 2 2 3 3 4 4 and this one. So F5. So you have 5 5, right? Or 5. Then return, right? Return. Then R0 will have 5 5. Okay, 5 5. Then you are just copying R0 return value to R1. What did I do? Okay, here. Okay. Okay. Okay, any questions so far? Okay, so let me recap what we have done so far. Here. So what we have done so far. So we use a BLX instruction. BLX instruction to make a function call. At the same time, to change instruction set. Okay. So one missing thing is how to return when you return back to the caller. Right? When you return, okay, show you this code here. So sum, right? Sum instruction set. So when you return, you are supposed to do instruction set change, right? You have to go back. Then sum instruction state to ARM state, sum state to ARM state. You have to, switch instruction set. So how that is done? Okay, that is done through BX instruction. When you return, right? Return. A little bit confusing, think about, normal function call. Don't worry, don't think about, instruction set switch. So you have a main, then inside here you are calling, function foo. Don't worry about instruction set change, right? Then you are calling this function, right? Then main, then you are calling this function foo, right? Then calling this function, execute it, then you are supposed to come back, right? And continue executing the remaining code. So when you make a function call, then you are supposed to use BL, right? Foo. So at the end, what instruction you have to use when you return back to this point, return location. So probably move instruction, move PC, then LR. Right, that instruction. So because BL instruction is jumping, right? First one is program counter will be set to the location of first instruction. Location, right? Location of first instruction in this function, right? Foo. And second, link register will be updated with this return location. So at the end, you are supposed to write this code, right? To update program counter, right? So in case of let's say foo instruction, foo is implemented using some instructions now, sum2. Okay, you added some directive and ask compiler to use some instructions to implement that function. Then what do you have to do? You have to use BLX, right? You have to use here BLX, and at the end, you have to use BX, then LR. Okay, instead of this, because you have to do instruction set change. branch and instruction set change. So that instruction is doing two operations. First, this instruction is doing what? This instruction is doing program counter will be updated, right? Only. And this one, program counter will be updated. And second, ISA change. Two things. One additional operation, ISA change. Okay. Okay, so here, look at this. BX, RM. Then you're supposed to use BX, LR to return back to the caller. Okay. But one more very important detail. Okay, this is the one. Okay, so this one RM register. In this case, LR link register. So LSB least significant bit of LR is 0. Then CPU will change it to or remain in ARM state. Okay, 1. Then switch it to, change it to, or remain in some state. A little bit confusing statement, right? But you know, it is very obvious operation. Let me explain. Right? So in this case, we are assuming, okay, in this case, we are assuming main is ARM. Main is an ARM state. And foo is in some state, right? Some state. Right? Then here using BX instruction, you want to switch from some state to ARM state. Right? What if that guy, what if this main is in some state and foo is in ARM state? So the function, this function, main in some state is calling ARM function. Then you are supposed to use the same instruction to return back. Then the question is, how do you differentiate between these two? Okay, ARM to sum to ARM. So how do you differentiate? You have to switch it to here, in this case, ARM state, or second case, or sum. How do you know? You are using same instruction. The return occasion is the same probably. If return occasion is the same, if one is the same, return occasion is the same, then how do you distinguish between these two? You cannot tell, right? CPU hardware cannot tell ARM or sum. Which one I have to choose? CPU does not have any clue, right? If you don't provide any information. So secret is this one, LSB, bit zero, okay, of link register. Link register is 0, okay, LSB, least significant bit, okay, last bit is 0. Then CPU will go to ARM state, okay, and LSB is 1. Then CPU will go to some state. That is the rule. Some. Okay, 좋아. RM의 마지막 비트를 고의적으로. Yes. Juan, probably hacker, right? Bad hacker, bad people will do that, right? So yes, yeah, that can happen. That you know, if you change LSB, deliberately on purpose, then you execute that instruction, then instruction set will be changed to arm or sum, right? Then then what would happen? Then you implement some bad code at that location, probably, right? So that is what bad hacker is doing, right? So Juan, let me finish this discussion. Then probably you can ask more question, right? So okay, so let me show you some demo. But yes, Daesung, yes, very good question, right? So that is the thing I'm going to, I'm trying to answer now. I'm trying to answer now. It is very strange, right? How come? How come you are making a function call, right? You are making a function call using BLX. That is very good question, and I'm trying to answer that. Right? So you are trying to make a function call using BLX, right? Foo. Then CPU will do two operations, right? First, program counter, right? That is obvious. Foo. Program counter, we change it. Then three operations, not two, right? Let me write it down. Here, let me write down. The first program counter will be updated with foo, KPLX. Then second, link register will be updated with the return location, right? And three, last one, ISA change. In this case, to sum, change it to sum. Okay, the thing, okay, 1, 2, 3. Okay, not this one. Okay, this one. Okay, so let's say A. Okay, so the strange thing is, okay, you have to take a look at this second operation, link register, right? Because when you return, you are using link register, right? Link register is updated with the return location, and in ARM state, okay, each instruction is located at 4-byte boundary. Okay, think about this memory, right? Memory. So addition, for example, okay, addition, subtraction, LDR, and so on, right? So first instruction, let's say this location is 0. Next instruction starts from location 4. Next one is start from 8, C, and 1, 0, and so on. So each instruction is located at 4-byte boundary. 4-byte boundary. Okay, meaning that if you divide this location by not divide, if you divide this location of instruction by 4, the remainder supposed to be 0. Remainder divide by 4, then remainder is 0, right? Divide by 4, remainder is 0. Remainder is 0. So 4-byte boundary. Then how come this link register could contain this condition, right? LSB is 1, then some. How that condition can be created, right? So LSB is 1, right? So let's say return location. Return location, let's say foo instruction is located. Okay, sorry, this one. BLX is the instruction located at 1000. Then return location is supposed to be 1004, right? So L link register supposed to have 1004, like this, right? But what it says, but what should happen? If link register contains 1004, when you return back, this condition is not met, right? Okay, so this condition is met, right? This condition, you are switching to ARM state. This condition. This condition, right? This condition is okay. We are returning to ARM, but think about, some code. This condition. Okay. From some state, you are calling ARM function. Then what would happen? Again, from some state, you are calling ARM function. Right? In some, instruction is 2 byte or 4 byte. So each instruction is supposed to be either in 4 byte boundary or 2 byte boundary. Okay, 2 byte boundary. That means, this 4 or that instruction is 4 byte. This one is actually 4 byte inside. So next instruction supposed to be located at 4. But the question is, this condition, we are talking about, second. LSB is 1. You are supposed to come back to, after executing this ARM instructions, you are supposed to come back to some state. But if link register contains this value, okay, 4 is what? Binary 0, 1, 0, 0, binary, right? 4. So LSB is 0. LSB is 0. That means you are returning to, you are going back to, some ARM state, not some state. See the problem? You see the problem? So someone supposed to change this LSB to 1. Not not this 1004, but 1005. Someone supposed to change their return location to 5. It sounds very strange, right? 5 is not in 2 byte boundary or 4 byte boundary, right? So when you return, actually that LSB will be ignored. The role, the purpose of this LSB is a switching instruction set. So CPU will ignore this LSB when you return, when you compute, when updating program counter, right? BL program counter will be updated with LR. But when CPU do this operation, this LSB will be ignored. It will be filled with 0. So this bit will be used to check that condition. Okay. So let me show you, demo. So this one. So who do you think is doing that operation? The question is, who do you think is doing that operation? You have to do that? That is too much, right? That is too much. Compiler will do that for you. So you don't have to worry about that. Okay. So let me show you a demo. So here, I think from here, right? This one, we are in ARM state again. Then calling ARM state and calling some function. Then return back, okay, to ARM. Then return location supposed to be, 4 byte boundary, and LSB supposed to be 0 to return to ARM state. So this one is not that interesting to me, right? To us, right? So I prepared, good example. So let me show you. Don't worry about this. Let me comment out this one. Okay, comment out. Let me remove this for now and show you this code. Okay, so this code from some state, right? We have directive. From some state, we are calling ARM function. Okay, some state. Okay, some state we are calling ARM function. Then after executing ARM function, you are supposed to return back to some state. Some state means LSB is supposed to be 1. We want to see that LSB. Really, compiler is setting LSB to 1. We want to see that, right? So here, so don't worry about everything. Okay, then so that is calling, right? Calling this guy. So let me set breakpoint here. Breakpoint, then make this function call. Okay, so let me compile it. Okay, then download it to the board. Okay, this one. Okay, now register. Okay, so let me set breakpoint. We don't want to execute line by line, right? So let me set breakpoint here. The breakpoint, then press F8. We stop here. Okay, so check out this CPSR. CPSR. Now we are in T is 1. And J, you don't have to worry about J, right? J, right? T is 1. So that means we are in some state. We are in some state. Some is calling ARM function, right? Calling ARM function. Okay. So now it is calling ARM function, ctest. Ctest. This one. We have this directive. So compiler will use ARM instructions to translate this C function. Okay. So let me execute F5 here. Now, right? BLX. Then you have to check the location of BLX, right? BLX is located where? Remove to crowded. Okay. BLX is located at which one? Program counter, right? 0, 0, 1, 0, 0, 5, 0, 5, E, 2. Right? 2 byte boundary, right? 2 byte boundary. Because you are in some state, right? That is located here. Okay. The next instruction. Let me check compiled binary. Okay, this one, this label, Control C, compiled one. Okay, so oh, cannot this one. Find. Okay, this one. So BLX instruction is located at 100. Let me remove too long. Okay. 0x1 005E2. And next instruction is what? Pop. Pop instruction is located at +4, right? +4 position. 1000 +4, 5, E, 6. Okay, 5 is 6. Next is pop. Okay, this pop is this. Okay, that instruction is located at 5, E, echo 6. 5, echo 6. Okay, so make a function call. You are supposed to have what? Make a function call link register. Link register supposed to have this one, right? Next instruction, the location of next instruction, 1005E6. But if that is the case, then we have a problem, right? You cannot, after executing the code, you cannot return back, right? Because of that rule. LSB is 0. then instruction set will be but you are, in some state, right? Instruction set supposed to be some state when you return. So LSB is supposed to be 1. That means this is supposed to be not 6, 7, right? Because 6 is what? In binary, 0, 1, 1, 0, 6, right? So LSB is supposed to be 1, right? This one supposed to be 1, so 7, right? 7. So let me show you. Now go back to here. Okay, here. So check out this link register. Okay, link register. Let me press F5. See? Link register 5E7. 5E, not 6, right? 7, right? Very strange number. Right? Okay. So if you look at the compiled binary, right? Compiled binary, then there is a secret, right? So okay, not I think compiled binary. Can you see? No. Okay. Okay, so that is the one. Okay, in this case, compiler is not setting. Okay, compiler is hardware will set. Hardware will set this LSB to 1. I think CPU. Right, you are make a function call. Right, make a function call, then return location. This return location supposed to be updated by hardware. Right, so hardware will compute, will update LR, but with what value? That is computed internally by hardware. So CPU internally add one to that location, because this is 4 byte. This instruction is 4 byte, right? So next instruction supposed to be located +4 at this one. But hardware knows, right? Hardware knows what? Hardware CPU knows, okay, I'm in some state. Hardware knows, right? By looking at J and T, J bit and T bit, hardware knows, okay, I'm in some state. When I return back, you are calling ARM function, right? ARM function, right? So I know you have to, when you return back, you have to change instruction state to some. So hardware will add, one to this. I think that is what happening. Yes. Okay, I think time is up. Let me stop here, then continue to talk about that interworking. Homework 5. What is homework 5? You don't actually you don't need some lecture, right? So we are talking about ARM state only in this assignment. Okay, don't worry about some state. Okay, ARM state only. ARM state only. Okay, assume ARM state, then do this assignment. So again, this assignment has nothing to do with today's lecture. Okay, this assignment, right? So I ask you to write your own debugger. Okay, we don't want to use that. Register, nice register, view. This guy is providing, right? Instead, we want to design our own debugger, right? after executing one instruction, each instruction, I want to see the register state. R1 register really changed to 17. Okay, so after that code, what I asking to you? So after that code, probably you add, okay, debug your own macro, your own debug macro. Then this macro will print out, registers, all register, these register state, register value. Okay, you want to check out, okay, R1 is updated properly. Okay, so debug your own macro here and debug own macro here too. Okay, here too, and check out. Okay, it's like printf statement, right? In C. Think about that when you design, when you write the first C program. How did you debug your program? You added, printf here, printf there, many places, right? Something like that. Your printf statement, right? Okay, that is the one. All right, any question before closing up? Juan, probably probably today's lecture, the lecture, the last lecture, right? Probably answering your question. Okay, then I'll see you next time. Okay, bye. Okay, thanks.